Yes, thank you, Michael, for the invitation to be here. It's a real honor. And I've really enjoyed meeting some of you already. Amazing stuff that's going on here. So this is a very special place. You're a big name in the universe of water and in the universe of environmental sciences. So it's fantastic to be here. And I'm excited to share some of our work with you. And I've batted back and forth with Michael, and I've secretly batted back and forth with you when I talk to you, those of you that I talk to today. I'm going to pitch this, and what I'm going to pitch of the many different things that we're doing. So we landed on presenting some of our work in my research group on groundwater-surface water interaction. And there have been a lot of people in my group that have been working on this particular case study. And I wanted to at least give them all the honor of being listed here. This is not work that's coming from me. I'm relying on a lot of people to help with this. And there's multiple communities behind this work as well. So understanding that you all come from many different backgrounds. Before I can talk about regulating groundwater because some fish die, I need to talk to you about why are we even managing water, right? It seems like, duh, of course we do water management, but why are we managing water? Do you know where your water comes from? In California, there is a lot of water use. In green is all these landscapes that are irrigated with water. In purple are all the urban landscapes that rely on water. And most of the water uses in the summer, some of the water uses in the winter. So this is where the water uses. Now, where is their water coming from? Well, it's all coming from precipitation. There's a little bit that comes from the Colorado River, the western Colorado River, not the one here in town. This is precipitation. This is where the water comes from. Do you notice how far away that water actually occurs from where the water is used? And also, we have all this rain in the next 3 months. We don't have nothing come April. April to October, we're in drought, period. No precipitation. When do we need the water? Well, when we're in a drought. So we got a disconnect here. We got water where we don't need it, and we got water when we don't need it. To bridge that disconnect, we need water management. We need tools to store water from the winter for the summer, and we need tools to bring water from the north to the center and the south. So let's first talk about water storage. There is one big storage reservoir, snow. Because when it snows, it's not running away, it's not infiltrating away, it just sits there. It's a giant storage reservoir. 20% of our precipitation can sit in that reservoir all winter long until spring when it melts off. Then think about what's under those trees. Some of you work on this. There's a lot of soil under those trees. Half of the precipitation just sits in the soil, waiting to be picked up by a root in March or April when the trees start sprouting and the grass starts sprouting, and can use that water that's sitting in the soil for evapotranspiration. So half of the precipitation just gets stored in the soil. It's a huge reservoir to then later be transpired by a plant. And then in California, we've built a lot of reservoirs. 20% of that precipitation can go into these reservoirs. And in those reservoirs, we can store water, we can put all the knobs and push all the buttons to regulate how much we want to have in there, how much we want to release, when we want to release it. This is a great reservoir. This is the one we actually manage. We can do nothing about the soil, we can do nothing about the snowpack, except for maybe change the climate. This is the one that we can actually control, and we can put the levers on, okay? So we got all these reservoirs to hold on to water from the winter for the summer. Now, we also need to bring that water from the north to the south. How do we do that? We need transportation pathways. Some of them are natural. We got this incredible geology and geography in California where the Central Valley, which is this big basin here in the middle, actually is a watershed that covers this white line around here. This watershed covers practically a third of California. And most of the precipitation, except for that precipitation that's in the far northwest on the coast, most of the precipitation is in that Central Valley watershed. And all of that water would ultimately end up right here under the San Francisco Bay Bridge. That's where it all gets collected. And that's a massive transportation system that we take advantage of. And then to that massive transportation system, we add lots of canals to move water around, not only the Central Valley, but the entire state all the way to San Diego. So we have a massive water transportation system in the state that's hooked up to that delta near the San Francisco Bay to move water around. That's what water management is about. Except there's those years where it doesn't rain, and then there's another year after that it doesn't, then there's a third year that it doesn't rain. We have the most variable climate of all climates in the country. We have more variability in precipitation than anywhere else, even worse than here in Texas. And you have some of the most variability in stream flow here in Texas. So do we. So some years we could be really good, some years we are really bad. We don't have enough storage in the snowpack or in the soil or in those reservoirs to keep water from the wet years for those 5 or 6 dry years that may be coming down the pipeline. And so, especially the last 25 years, we've been sticking in a mega drought, and we're in a massive precipitation deficit. And so what have we done in that time? And I'm somewhat oversimplifying. We've captured that 4th reservoir that we have. We talked about snow, soil, surface water reservoirs, groundwater. That's our biggest reservoir. That's where we actually have most of the water sitting. And when it gets to be not enough water in the river, or when there's no canal coming to your farm or your city that brings surface water, you drill a well and you just pump the water out of the ground. So that's our 4th reservoir. And with these dry years, we've been massively using that groundwater. And while a single wet year can keep us from, let's see, I'm looking for my mouse here. Just getting oriented. There we go. So Northern California last year was pretty wet. Southern California was pretty dry. The green and yellow is indicating that groundwater levels haven't changed much. The red and orange is indicating that groundwater levels went down. And so you see a dry winter, groundwater levels next year go down. A wet winter, groundwater levels mostly stay steady, come up a little bit. But with all of this precipitation deficit over the last 20 years, everything that's in brown here has seen significant average decline in water levels over the last 20, 25 years. So this has had huge consequences on people that depend on groundwater. Lots of domestic wells going dry, lots of land subsidence impacting primarily the water transport infrastructures, with canals no longer being able to transport water on that water pipeline, seawater intrusion, and other impacts. That all screams for doing something about how we use that groundwater reservoir, that groundwater storage system. So in California, we've thought about for over 100 years how to regulate groundwater. And to the degree that the legislature hasn't done anything about it, people have gone to court, and the courts, they use common law doctrines to decide on these cases. And in California, the courts have established over 100 years ago that if they're going to have to decide who gets how much groundwater, the rule is one of sharing. It's not one of capture. So what gets shared is the renewable part to groundwater. We call it the correlative rights doctrine. Everybody has their fair share to the renewable part of groundwater. So you can already see that we're using more than just the renewable part of groundwater, which is why groundwater levels are going down. And few people would want to go to court and then find themselves in a position where they're going to have to use less water. They want their neighbor to use less water, but they don't want themselves to use less water. And if they go to court, then they're going to have to share the shortage. So we've been in a situation for over 100 years where, yes, the courts would decide that we all share only the renewable part of groundwater, but No, there wasn't really a law that made sure that everybody abides by the law. So thinking about laws, I wanted to give you what I learned over many years, sort of what governance actually is all about. I'm going to give you my Administrative Governance 101 class here. Think about speed limit as one regulation. And let's think about the key elements to that regulation. Somebody found out that objects moving too fast on a road is a problem. Health issues, economic issues. So there was a big problem. The goal was to run a smooth economy while keeping people healthy, and so we needed to have a way to keep things sound on the roads, and that way was to control the speed. So we identified a primary responsible party, which is the driver. They get a training program before they get a license to drive, and the driver has management tools to control the speed. The driver also has a speedometer, a monitoring program, so that the driver always knows how fast they go. And then on that speedometer, there's a red line that says, here's the speed limit. Or on the road sign, it says how much you can go on your speedometer. And then you use your brake pedal and your gas pedal to be not above that speed limit. So we have management practices, brake pedal and gas pedal. We have monitoring system. We have that speedometer. We have a responsible party that manages the system. And then we have enforcement. Without enforcement, why have a speed limit? And the enforcement in this case is that you have a cop pointing at your car, and you're going this fast and you get a ticket. We don't have yet the government having a GPS on every car, and at the end of the year, you're going to get your ticket for X many minutes being Y many miles per hour over the speed limit. Which we could do. I mean, that would be a choice, right? And there's a political reason why we don't do that. Those are the key elements to regulation. So let's apply this to groundwater. So in California, with all these incredible things going on that were very damaging to society, there was an outcry for things to be done. That's kind of an oversimplification, but basically things needed to get done. And in 2014, 100 years after we tried this for the first time in the California legislature in 1914 and failed, in 2014 we passed the Groundwater Management Act, the so-called Sustainable Groundwater Management Act, or SGMA. Thinking back to regulation, there has to be an objective, right? In this case, the objective is to maintain, the choice of the legislature was that we will honor what the courts have always decided, which is that groundwater, the right to use groundwater is a right to use an equitable share of the renewable part of groundwater. And the legislature extended that to say, we're going to make the objective of groundwater management for groundwater to be sustainable. That is, groundwater resources to be usable by future generations in much the same way we're able to take advantage of that resource today. So that was the goal. We could have chosen differently, but that was the goal we set. We also identified who the trucks are and who the cars are. We have different speed limits for trucks than we have for cars because trucks are a bigger risk than cars. What the legislature did is they defined that of all the groundwater basins in California, which is everything in light green and dark green and orange and in yellow, only the medium and high priority groundwater basins, those that actually have a significant groundwater use, would have to do groundwater management. So we have sort of this diversified portfolio, and there's basins that don't have to do anything, there's basins that do have to do anything. The basins that don't have anything is like the pedestrians don't have a speed limit, and then there's the basins that have to do something, and then there's basins that we call critically overdrafted that have had a long history of way too much groundwater use. Those are the trucks. They have to move a little bit faster than everybody else, right? Because they already have a critical problem. So that's one pillar of SGMA, sustainable groundwater management everywhere where there's significant groundwater use. The second pillar of SGMA was, no, it's not the state that's going to make these regulations and that's going to sit down and prescribe exactly who does what. It's going to be up to the locals to decide how they want to do this. So the second pillar was local control. And as a result, we ended up with about 250 local groundwater sustainability agencies about 3 years after this law was passed. An incredible administrative effort to create these public agencies from existing public agencies that would manage about 100 groundwater basins, and they wrote about 150 groundwater sustainability plans. So there's actually now layers of regulation, because the other piece of this is that we have these local groundwater sustainability agencies that actually are the cops on the street. But what these cops on the street do, and they plan like what the speedometer is going to be and what the speed limit is going to be, but there was the state sitting behind it to oversee these local agencies to make sure they are not trying to squirrel out from under this mandate of sustainable groundwater management. And so there's oversight by what we call the Department of Water Resources. That's a mostly technical agency that provides also technical assistance. They are the primary oversight of these local agencies, and if they find that the local agencies aren't either preparing a proper plan or not implementing that plan properly, they, according to Chapter 11, and not incidentally so, Chapter 11 of SIGMA says if a local agency doesn't perform properly, then that local agency comes under the direct control of what we call the State Water Resources Control Board, which is a regulatory agency, has a lot of enforcement experience because they are managing surface water rights and water quality, and they will basically then step into the basin and cut everybody off to the degree they think they need to cut them off of groundwater pumping. So we have these controls in place, and in this scheme, we then have the driver being sort of a combination of this local groundwater sustainability agency, who's both a cop and a driver, and the individual groundwater pumper, who's the real driver of this. And then between the local pumpers and the GSA, the Groundwater Sustainability Agency, they're going to have management tools, the gas pedal and the brake pedal, and they have to have monitoring tools. And that all has to come together in a plan. That's the groundwater sustainability plan, and everybody was required to finish those by 2022, the critically overdrafted basin much earlier. So in that groundwater sustainability plan then, you have a description of what's going on in the basin in terms of hydrology and land use and water use and how much water is there and what has happened with water tables and what's happened with land subsidence, etc. You have, because local control is so important, you have an explicit description on how stakeholders are being engaged, how things are communicated. You describe how you monitor your speed. You describe your monitoring networks. You describe what your thresholds are, your speed limit, and why you pick that speed limit, and how that speed limit is protective of undesirable risk outcomes. And that plan spells out the gas pedal and the brake pedal. The gas pedal being to do groundwater supply enhancements, that is managed aquifer recharge, and the brake pedal being to reduce the amount of groundwater use in one way or another. Those are the basic elements that go into a groundwater sustainability plan. Now, in the case of California SIGMA, we actually have 6 sustainability indicators, because the legislature said sustainability means you don't have undesirable results, and undesirable results means no lowering of water levels, no lessening of groundwater storage, no decline in water quality, no land subsidence, no seawater intrusion, and no further depletion, no additional further depletion of surface water due to groundwater pumping. We need measurement tools. We need a speedometer for each one of these sustainability indicators, and these local agencies have been asked to define their so-called minimum thresholds, their speed limit, specifically for each of these sustainability indicators. Of course, if you're not on the ocean and you don't have seawater intrusion, you can skip that one, right? And if you don't have any land subsidence and you can show that you will never have land subsidence, you could skip that one too. But everything else needed to be addressed. And the part that I want to focus on in this talk is that last one. And I want to focus on that one because for all the other ones, we can very quickly, if we did a brainstorming session here, come up with What would be a good speedometer? About water levels, speedometer would be the monitoring wells that we can, or the wells that we already have in a basin. We look at the depth to the water level, we monitor that. Same with groundwater storage. If we know how much the water levels change, we know how much groundwater storage changes. Water quality, we can go to the wells and measure what the water quality is. Seawater intrusion, we can go to wells and see whether we see any seawater in it. Land subsidence, we have satellites and geosystems that measure land subsidence for us. Groundwater surface water interaction, how do we do that? Before I go into that, let's kind of look at what that actually is. For those of you that are not hydrologists or groundwater hydrologists. So when we look at this interconnected surface water that's connected to groundwater, we talk about this situation on the left. And we generally divide this into a situation where the stream is actually gaining groundwater and a situation where the stream is losing groundwater. What you see on the right is a small 2-mile watershed in the Coast Ranges about 3 months after it last rained in California. No rain for 3 months. It's still running 2 miles, to the top of the mountain from here. It's still running. It could not possibly be runoff from the last rain, because there's no way that it would take 3 months for that last rain to run over the landscape down the creek to this point where I took this little video. So what is it? Well, it's groundwater. It's groundwater that's oozing out of the mountainside and out of the soils and is going into the stream along that 2 miles of that stream, and it's this much over those whole 2 miles. So it's a little bit under everywhere, so to speak, right? That's an interconnected stream. And when I put a well next to this stream, if I were to put a well 10 or 20 feet from that stream and I started pumping into that well, then this water level over here would go down near the well, and instead of water going into the stream, I would all of a sudden be sucking water from that stream into that well, right? That's what we're concerned about when we talk about managing groundwater relative to stream flow. It's this, what hydrologists call base flow of a stream, that comes from groundwater when there isn't rainfall or reservoirs that are feeding the stream primarily, right? So that's what we're concerned about. And the place that I want to look at is the place that got an A+ card in this year's groundwater assessment when it came to that map that I showed earlier, which shows groundwater level changes over the last 20 years, which is that place up in the northwest corner of California. It's a small valley called Scott Valley. And it's the only place that, one of the few places in the entire state that hasn't seen chronic decline in water levels for the last 20 years. And you would think that under the Sustainable Groundwater Management Act, they're gonna get their get out of jail for free card. They don't have a problem. Why should they even think about groundwater management? I mean, there's no chronic overdraft of groundwater. So let's look at this. So this little valley has a stream that comes off of 8,000 feet high mountains on the west side that carry a significant snowpack. Mostly Paleozoic sedimentary rocks, fairly impermeable rocks. And by fluke of nature, there's some faulting here in the valley and as well as here that has basically dammed up the river, and over the last so many tens of thousands of years, has created this alluvial basin that's nestled at 2,500 feet above sea level in the mountains. It's a beautiful valley. So many of you have some geologic background. So when I look at this flat landscape sitting in these mountains, I always think of a bathtub that's filled with sediments. That's what this is. The bathtub is about 250 feet deep at the deepest place, 300 feet at the deepest place. Mostly sandy, silty sediments that have been deposited by the river and washed off the mountains. This river feeds into the Klamath River, one of the largest West Coast rivers, a prime salmon habitat. And this particular valley is a prime spawning ground for coho salmon. Endangered species, protected. And one of the problems that's been identified here about 20 years ago was that the groundwater pumping that goes on for irrigating pasture and alfalfa in this valley has significantly impacted stream flow, which in the summer seems to be quite a bit lower than it used to be. So the beneficial uses that we're looking in this valley here are both the irrigators that are diverting surface water, the irrigators that are pumping groundwater, and the fish that are in the stream. Plus then, you have other ecosystems that are important, not just the fish, that all want some of this water that's in this basin. So if you look at the stream flow in this basin over the last 80 years, you will see there's not really a significant trend of any kind, except that sometime in the mid-70s, those summer flows suddenly started to get lower. Well, that time in the 1970s coincides with when USDA gave the farmers a whole bunch of money to improve their irrigation efficiency. They were all flood irrigating their pastures and alfalfa fields, where the alfalfa gets cut in May, then it gets cut again in June, and then because they didn't have any water, they were all relying on surface water. By mid-July, that snowpack was gone. Actually, by July 4th, the snowpack was gone. They dry out the alfalfa, they do their second cutting, and they go home. In the mid-70s, USDA supported these farmers to go to from flood irrigation to sprinkler irrigation on wheel lines. So they all needed a pump to pressure up the wheel line. And once they had a pump, it was an easy step to just drill a well and hook up that pump to a well, and instead of relying on stream flow for the irrigation, to actually just pump it out of the ground. No longer you needed a canal, you didn't have to wait for the irrigation master to show up, and most importantly, you didn't have to stop irrigating on 4th of July because there was no more water in the stream. You could actually start irrigating again after the second cutting and through August do a few more irrigations and get a third cutting out of it for your alfalfa. That's what they did in the 1970s. And our minimum mainstream flows went from about 40 CFS to about 20 CFS. And that difference is just about 8 inches over 13,000 acres of alfalfa on a third cutting. That's almost an equivalent amount of water. So what we're seeing in lower flows almost is exactly what is irrigated for that third cutting on the alfalfa. So there was a clear connection between switching to groundwater pumping and what the flows are in the stream and how they impact the fish. Moreover, then over the years, people have tried to address this. There's the Endangered Species Act, which protects the coho. There's the Clean Water Act, which was used to protect the fish because you have high temperature discharge when you don't have groundwater flow into the stream. So basically, this was an indirect way to get to the groundwater pumpers to actually get lower stream temperatures by having more groundwater inflow to the stream. And then we also have what's called the public trust doctrine, which basically says, even if everybody operates under existing water rights, ultimately, in a navigable river, when there is an impact to environment, that ecosystem is in the public trust, and it can't be given away. And so if the state accidentally gave away water rights that impact these ecosystems, the public trust doctrine gives the state the right to roll back these accidentally given out water rights. And again, I'm oversimplifying here. But basically, the public trust doctrine is a way to roll back on existing rights for surface water diversions, or if there were groundwater rights on existing groundwater rights, to protect the stream. And in 2018, the courts decided that does apply to groundwater pumpers as well if they're impacting the stream flow. That was a really important decision. So we have that in addition to having the Sustainable Groundwater Management Act, which means that really what we need to do in this valley, even though it looks like the last 20 years things haven't changed very much, we actually need to roll back in time and provide more stream flow and make a reversal of stream depletion. We need to work on this interconnected surface water and come to a reversal. So how do we manage this? We need a meter. That's the first thing, right? We need to figure out what this is. Let me go first to the definition of the minimum threshold for depletion of interconnected surface water that's in the legislation. The minimum threshold shall be the rate or volume of surface water depletion that is caused by groundwater use, not by surface water diversions, not by climate change, not because it rained more or less last year. It's the rate or volume of surface water depletion that is caused by groundwater use, that is by groundwater pumping. and only to the degree that it has adverse impacts on beneficial uses of the surface water and may lead to undesirable results. I've already identified the beneficial users. Those are both the irrigators and the fish in this case. I haven't identified adverse impacts yet, so we're going to have to do that as part of this. Let's focus on that first part. One other thing that was in that legislation was that nothing before 2015, no undesirable results that existed at the time the legislation was passed needed to be addressed. It could be addressed by the local agency, but they didn't have to address existing bad conditions. But they just couldn't get worse in the future. So we actually have to, in this process, distinguish not only between not only these adverse impacts and identifying which part of the stream depletion is due to groundwater pumping, we also have to identify which parts are from before 2014, which parts are from after. Except that we do have that public trust doctrine, and if under the public trust doctrine fish are protected, then that 2014 deadline is irrelevant. We have to go back to the 1960s, possibly. So rate or volume of surface water, let's look at that. How do we measure, if somebody turns on a pump, how much that volume would be? I mean, even just measuring that flow from the subsurface to the stream or from the stream to the subsurface is difficult to measure. There's not really a single instrument to this with on a basin scale level. Modeling is typically sort of the choice to do. There's some analytical simple models, there's more complex integrated models, but it's very expensive for local agencies to develop that. So many agencies have chosen, because they have that 2014 grandfathered in limit, have chosen to just say, we're going to use groundwater levels as a proxy to determine whether we have more stream depletion than we had prior to 2014. And basically what they're saying is, as long as our groundwater levels aren't any lower than they were in 2014, we don't have more depletion than we had in 2014, because it's that lowering of groundwater levels that causes the depletion. So we have all these plants that are basically saying, we're going to stay at levels that are higher than we were historically, and that automatically makes sure we don't have more stream depletion than we had in 2014. Other basins have the advantage of having dams and controlling their stream flow with dams, or they're so far away from pumpers that their groundwater surface water connection isn't impacted. Or they're already doing a lot of projects that are recharging their groundwater to levels that they don't have to be worried about their groundwater surface water connection. So that wouldn't apply there. In Scott Valley, we got all these complexities, different pumpers, we got lots of streams, we got variable recharge rates across the basin. So using simple water level measurements to figure out whether we can measure the depletion due to groundwater pumping with just monitoring wells, very quickly turned out to be not possible. We really, really need a model. So, for that groundwater use part and how that affects stream flow, there are some simple but very important and very relevant analytical solutions that have been used, mathematical equations that you can throw in your spreadsheet, and you can, if you know your aquifer properties and the distance to the stream and how much is being pumped, it will tell you how quickly your pumping is going to impact the stream and by how much it's going to impact the stream. Those are great in wet areas like Michigan, where this is used for permitting groundwater pumping. We've developed this for the Scott Valley to develop sort of the time scale over which stream is impacted by different wells. But the situation is way too complex to deal with stream drying out. When the stream is dry, then there's no impact to the stream. So what then happens to that impact that should be on the stream? What's going to happen to that? One important part that we really need to consider is the question to answer is depletion is the depletion to worry about is that's due to groundwater pumping, which really is about the groundwater pumping and the land use that's connected to the groundwater pumping. Some ET from the land surface, right? And the question is then, if I stop that groundwater pumping, I don't have that ET from the land surface, how much more stream flow would I have? But it's not just that. It's not just turning the pumping off and not having ET. It's really about, if you think about it, it's also really about what's happening with this landscape in the long term when there is no groundwater pumping. Am I going to irrigate with surface water? So am I going to have a surface water diversion instead? Am I going to have natural vegetation, some bunch grasses that have 10-foot deep roots and are themselves sucking up groundwater when they need ET? I actually need to implement, I need to know something about groundwater used by the natural vegetation when I think about what is the contribution of a groundwater pumping to stream depletion versus what is the contribution of natural vegetation to stream depletion. So I need to think about that when I do this. I need to think about climate change. Part of what we were showing in a thesis by Sprichik a couple of years ago is that in red you have the, actually I should say, the green line is basically the stream flow 1940s, 1950s, 1960s on the Scott River. The red line is the stream flow from June to December on the Scott River, 1977 to 2000 on the left, 2000 to 2021, mega drought on the right. The blue line is what the stream flow would be if we didn't do the groundwater pumping. And this is based on statistical analysis in this case. So basically, the reddish part is the stream depletion that's due to groundwater pumping, the reddish shaded area. The bluish shaded area is stream depletion that's due to climate change. So that's another piece that we need to figure into the equation when we make management decisions. And then on top of that, we're dealing with existing water rights. We actually have a groundwater adjudicated zone in this basin. And the adjudicated zone is not governed by the local groundwater sustainability agency. They have their own, they actually don't, in this case, don't have a water masters, but the local GSA, the local groundwater sustainability agency, has no regulatory enforcement capacity over the adjudicated groundwater zone. They also don't have anything to say for surface water diverters, which also impact stream flow, of course. So all of this is really calling for a big model, integrated hydrologic model that we use as a measuring stick. But now imagine your speed limit, your driving habits weren't measured by a radar gun that's pointing directly at your car, but actually somehow the police had a computer with a big AI system that scours the internet for your LinkedIn posts and for your Facebook posts and for your other social media posts. And based on that, they do big AI and they figure out, oh, on the average over the year, you're going about 3 miles an hour too fast. So you're going to get a $300 ticket a year. And you're going 8 miles per hour too fast based on what AI tells you about your social behavior and how you probably do in traffic. So you're going to get an $800 ticket. How would you feel about that? Right? If that's the only way they can regulate the speed, you would want to be in the room when these things are decided, and you want to have some say in what's going into this model that's modeling your social behavior and whether the model results actually have anything to do with how you're doing, right? So when we use models as measurement systems that drive regulatory decisions and potentially fines, you have to have everybody in the room. This is what's called a co-laboratory, where you have models that deal with all of the different aspects of what's being regulated, and I would call this a transdisciplinary co-laboratory, because not only is it a bunch of scientists from different sciences, that would be an interdisciplinary co-laboratory, you have to deal with all the stakeholders and interested parties as well. So in the Scott Valley, it's all these things that have to be at the table to decide how to do this in our groundwater sustainability plan, because that's still what we're talking about. So we have stakeholders, we have science, we have managers, and we're talking about not just groundwater, we're talking about surface water, and we're talking about ecology in order to set the speed limit. We put together all these data. We've got lots of data, groundwater level data, stream flow data, weather data. We put all that together. We have maps of land use, maps of irrigation systems, and where there's surface water use and groundwater use. We know where the wells are. We know something about hydrogeology. We built this huge integrated hydrologic model over the last 15 years. And when we first came out with this 10 years ago, we showed it to the so this model is showing us what amount of exchange is actually happening at that groundwater surface water interface. So we showed the results to the stakeholders. This is a map that shows stream flow in average stream flow in various months throughout that system. Imagine, I mean, we have stream flow measurements everywhere in the system, and we can make similar maps of that groundwater surface water exchange in that stream flow system. We showed this to the stakeholders, and they say, well, what's your input? And we told them, well, we think that you're irrigating 30 inches a year on the alfalfa, and you have this much ET, and they're looking at me and saying, Harter, we're not irrigating with 30 inches a year. There's no way we could possibly get 30 inches of water out of these sprinklers. And the local farm advisor, my colleague, my extension colleague in the county, stands up and says, well, tell me what the valve size is on your sprinklers and how often do you change the sprinklers out? And he does back of the envelope calculation, comes up with 24 inches of irrigation every summer. And we're like scratching our head, okay, now we have a problem. So he starts a research program as part of this transdisciplinary co-laboratory with growers and some other scientists that look at ET and soil moisture and how much irrigation happens in this valley. And we got new data that we were able to input into the model and run a new model with it, do an excellent calibration with this, and make predictions on this. So in the model development, we engage with stakeholders. And the stakeholders includes tribes, it includes farmers, it includes environmental groups, it includes environmental justice groups, it includes downstream fisheries. So now we have a meter, which is an integrated hydrologic model. It's not only providing us with 10 data points or 20 data points, it's providing us with data points every 100 meters in this 50,000 acre valley. We have those data points for every day of every month of 30 years. And we can now run scenarios, future scenarios on this 30-year time series where we tweak something in the valley. We tweak what we grow, we tweak how we irrigate, we put in recharge, we build reservoirs, we can put that into the model, we rerun the 30 years, and we can measure what the difference is everywhere in the valley in terms of water levels, everywhere in the valley, stream systems in terms of surface water and surface water depletion, and in terms of that interchange. Our stakeholders are overwhelmed with data. So what do we have to do? We actually have to sit down and ask them, what do you actually need to know? We got so many data, what do you need to know? They, of course, are interested in the environmental community and the regulator and the people that use the public trust doctrine for environmental protection. They're interested in fish and what the fish needs. The growers already get their irrigation. Now the fish in this place, they're depending on what we call functional flows. We have low flows in the summer, high flows in the winter. There's a shoulder on the flow. This is the stream gauge at the end of the valley. And sort of, this is a simplified functional flow diagram that sort of shows the many different functional flows that fish need over the year. This diagram looks very much like, the previous diagram looks very much like the one on the left here, which is the actual stream flow hydrograph at the outlet of this valley where we have this old stream gauge for 80 years. And we have the shoulder in the fall, we have snowmelt shoulder in the spring, we have a low flow base in the summer, we have high flows in the winter. All of these flows have different functions and the fish are adapted to these functions. So what the stakeholders told us, don't give us all those data right now. We really want to focus on what's happening at this gauge at the outlet of the valley, which we've been looking at for the last 80 years as sort of a proxy to everything else that's going on in the valley. So what we then did is we ran a lot of these scenarios for the stakeholders. We discussed with them the results that they needed. We proposed some results, explained to them. I just was back up there 2 weeks ago to do a training session on how to look at the graphics that we provide and look at these. And then we've also had some supporting research. This is great work that Claire Kuba just published that actually makes a quantitative connection between these shoulder flows and the summer base flow and how successful the fish are in spawning in the valley. So that work has been done and is ongoing. And we use all that to run future scenarios where we do more irrigation or less irrigation, as I said. I already mentioned that we need to account for a proper natural system, which also has groundwater use. And we need to account for this public trust doctrine in setting a threshold. So we're not just setting a threshold at where we were in 2015. We actually have to reverse that threshold. And one legal aspect of the public trust doctrine is It's not an absolute doctrine. It doesn't say that if you divert water from a navigable stream that has an impact on the ecosystem, it's not going to cut you off that water right. The city of Los Angeles diverted water from Mono Lake in Eastern California for a long time and was under the public trust doctrine told that they're going to have to curtail their diversions. Not completely, but they had to come to a compromise with the state that balances the public interest, which is the ecosystem, the public trust, which is the ecosystem, and sort of the public interest, in that case of Los Angeles, of having some water for their people to drink. In our case, for the farmers to have some water for irrigation. So it's a balancing process between how much do we give to the fish and how much do we give to the farmer. And so now the economics come into play, the economics of the fishery, also values for tribes, and economics of the farmers in setting where we needed to be in 20 years in terms of this minimum threshold, basically the minimum depletion that we needed, the minimum depletion reversal that we needed to achieve within the next 20 years. So running these different scenarios, enhanced recharge, changing crops, changing irrigation efficiency, changing irrigation schedule, building reservoirs. We ran all of those. We looked at many different outcomes. This is sort of a summary of these outcomes in terms of stream depletion reversal. And we ended up saying, among a committee that was officially appointed by the GSA, the majority of the committee said, we think the managed aquifer recharge and in-lieu recharge is the most economic way to do something about this problem. And at the very least, that should be implemented, and that will gain us 20% back from the existing stream depletion. We passed that groundwater sustainability plan. There was legal wranglings around the public trust doctrine, and environmental groups went to the state regulatory agency, and the state regulatory agency said, no, that's actually not enough. We're going to go ahead and curtail your irrigation schedule when the stream flow is getting too low after July 10th. We want you to cut back your irrigation by about 1/3. And so they wanted much more stream depletion reversal, and that's where we currently are, and that's probably where we're going to sit with the spacing. So what has made this story somewhat successful and failing at the same time? Some of it is that we've provided a lot of documentation. We've been working with all the stakeholders over the last 10 years, 15 years now. We've been trying to be fairly transparent about the model, what goes into the model. The model is available for others to use. People have had varying opinions about this. There's now a paper out from a social scientist. There's actually going to be a second paper from another social science group that's interviewed stakeholders and looked at stakeholders and asked them how do they feel about this somewhat informal, not official, transdisciplinary co-laboratory. But transparency and building trust, in my experience, have been the key pieces in developing a successful, what I would call a transdisciplinary collaboration, a successful collaboration with many different stakeholders. They're looking at a model as a regulatory decision support tool and as a regulatory tool. So that's where we are in this story, and we're going to continue working on this because the legal wranglings will continue. The link on the left is to our group's website, and I want to do a shout out for a beautiful podcast that Bridget and I put together in her Water Resources podcast series. Look that up. Thank you very much.